Cool. Okay, so today guys, we're 3D.2. Now you'll notice these 4 examples we're going through, these are actually the textbook questions. So we're doing question 1 and 2 from the textbook, and there is only 2 questions. But what we're going to do is supplement these questions with a booklet. And the reason is this is a very common type of exam question. It's really drawing out the relationships between the function, the first derivative, and the second derivative. And it's a very common exam style question. So this booklet is a collection of old exam questions. So you can we've said you can expect a conjecture question, definitely a conjecture question in the test. There will definitely be a graphing question in the test. And you can anticipate it's probable that there will be one in the exam as well. So the first thing I want to point out to you guys, and that we'll read through and emphasize to make sure we all understand, is this table here. This is like the foundation of all applications of calculus. This is the most important table that you'll look at for this unit. And what it is it's a summary of what the function, the first derivative, and the second derivative reveal to us. So we've got, if the first derivative is 0, okay, that means the slope is 0. If the slope is 0, that means it's not increasing, it's not decreasing. We have a stationary point. A stationary point could either be a maximum, a minimum, or a stationary point of inflection. All of those will occur when the first derivative equals 0. If the first derivative is less than 0, okay, the function is decreasing. That means if we have negative slope, the function is decreasing. In the next row, if we have positive slope, the function is increasing. So that's what the first derivative tells us. Then we move on to the second derivative. If the second derivative is equal to 0, we have a point of inflection, provided the sign diagram changes sign. That will include both stationary and non-stationary. And then if the second derivative is negative, the function is concave down. If the second derivative is positive, the function is concave up. Now what we're going to do is use this table in reverse. We're going to look at the function and go, oh, okay, it's concave up, therefore the second derivative is positive. Okay, so we're going to start with the right-hand side of the table and work our way back to the left-hand side. So question 1 here, we're given a graph. Use the graph to sketch graphs of f dash of x and f dash dash of x, clearly indicating axes, intercepts, turning points, and points of inflection. So this here, we should be familiar with this. This is a quadratic. All right, we recognize that by the parabolic shape that it has. And what we have is a stationary point here. It's a local minimum. And because it's a quadratic, that's going to occur exactly halfway between these 2 roots. So what's going to be halfway between -2 and +4? X is 1. So that's where that turning point is occurring. Now we're going to graph the first derivative. The first piece of advice I can tell you is draw the sign diagram of the first derivative. So once we establish that point's occurring at 1, what we can see is that we have negative slope. We're decreasing until we get to x is 1, and then we're increasing. So we can get the sign diagram of the derivative function just by looking at the original function. Now we expect this to be the case. If we're going to graph this function, right, if this is a quadratic, and if we differentiate a quadratic, we get the equation of a line, okay? So that means when we graph this new function, it's going to be the equation of a line. It has a root at x is 1, and it goes from below to above. The equation of a line. That's the graph of the derivative function. All right, I'll draw out how I got that again in a sec. So what we've done is we've recognised it's decreasing, so we have negative slope, and then it's increasing, so positive slope. Now that means the graph of the first derivative is below the x-axis and then above the x-axis, and we know it's the equation of a straight line because when you differentiate a quadratic, you get the equation of a line. Okay, let's move on to the second derivative. So now I want to draw the sign diagram of the second derivative. And what we should see is that if we're looking at this, the function is always concave up. It's always concave up. It doesn't have any points of inflection, which means there's no roots on the sine diagram of the second derivative, and it's always positive because it's always concave up. Now, let's think about this in terms of if we differentiate a quadratic, we get the equation of a line. If we differentiate this line here, if we differentiate that, we're just going to get 2a, which is just a number, and it's a positive number. Now we know that the coefficient a is positive because this quadratic is initially opening upwards. So if it's opening upwards, the number out the front has to be positive. So when we differentiate, all of those are positive. In fact, the graph of the second derivative is just a horizontal line. It looks like this. We're not exactly sure of this y value, but we know that it's positive. All right, so all we're required to do is demonstrate when we differentiate a quadratic, we get a line. When we differentiate a line, the equation of a line, we get the horizontal line. This is y equals, for example, if we have x squared, we differentiate x squared, we would get 2x. If we differentiate 2x, we get 2. So for example, y equals 2 in the circumstance that a is positive 1. Okay? So, let's move on to the second example. So, always sketch the sine diagram of the first derivative. Now what we can see for this one is that we have two turning points. We have a local max and a local min, and we do have a point of inflection. So we should be able to look at the graph and see those features. So we have max here, we have a min here, and we have a point of inflection. It's non-stationary point of inflection at x is 0. So we can see those features from the graph. Let's look at the sine diagram of the first derivative. We're increasing until we get to this point where x is minus 1. Sometimes there'll need to be a little bit of guesswork. Generally in an exam question there won't be. So we have x is minus 1 there. Here we have x is 0. And then the next, so we're increasing. We have positive slope until we get to x is minus 1. Then we have negative slope until we get to x is positive 1. Okay, a negative slope all the way down there. We don't have a root at 0 because the slope is not stationary at that point. It's decreasing over that whole interval, and then we are increasing after. Okay, so if we're going to graph a function like this, all right, we have roots at minus 1 and positive 1. It goes from above to below to above. That's what we expect it to look like. All right. Just label our axes, x, y. This is the graph of f dash of x. Okay, and again, one thing we should be thinking about is right here there are 3 roots. 3 roots means a cubic function. When you differentiate a cubic, you get a quadratic. All right, so we're starting to see those relationships appear there. Let's move on to the second derivative. So we'll draw its sine diagram first. And for the sine diagram of the second derivative, all we're doing is going, when is it concave up? When is it concave down? So we should be able to see we're concave down until we get to x is 0. It's opening downwards, so that means we have negative second derivative. Concave down corresponds with the second derivative being negative. And after 0, we have concave up. So that's going to be positive. And this is at x is 0. That's where the point of inflection is occurring. So what does that look like? Equation of a line goes from below to above. And we expect that to be the case. We've gone from a cubic to a quadratic to the equation of a line. Now, there's one really important point to emphasize here that will almost pop up heaps. It's going to pop up heaps. And that's what I've written in the very last point. The point of inflection on f of x is the stationary point on f dash of x, and hence the roots on f dash dash of x. Have a look. The point of inflection on f of x corresponds with turning point. All right, they have the same x value. Point of inflection, turning point, root. All at x is 0. So points of inflection on the original function correspond with turning points on the derivative function, correspond with roots on the second derivative function. Okay, so that's the first two so far. Let's spin around because I've drawn the other two on this side. All right. And let's sketch the sign diagram of the first derivative. All right, so we're going to have to approximate these x values because they're not provided to us. I'm going to say x is 1 is the maximum point, and then here we have a point of inflection at x is 2, don't we? All right, where it changes from concave down to concave up. All right, so x is 1, x is 2, x is 3, that's a root, that's not necessary for the first derivative. So what we can see is we're increasing, we have a positive slope until we get to x is 1. Then we're decreasing until we get to x is 3, and then we're increasing again after that with positive slope. Alright, so the graph of our first derivative then, x is 1, x is 3, and it goes from above to below to above. This is the graph of f dash of x. Okay, on to our second derivative. We'll draw the sign diagram. And we can see first, okay, so basically it just depends on which one you're doing, right? If we're doing the first derivative, we're asking questions about slope, right? The first derivative is all about slope. The second derivative is all about concavity. When's it concave up? When's it concave down? So we have a point of inflection at x is 2. We can see it's concave down before x is 2. And concave up after x is 2. So the graph of this one then, again, equation of a line from 2 goes from below to above. And we'll just emphasize that feature again, right? Points of inflection on the original function correspond with turning points. Okay, we have a turning point here, points of inflection, turning point, root. Okay, and we keep emphasizing that. All right, on to example D. Good, we're starting to get a little bit more complex here. And there's a couple of things going on here, right? We have a local minimum at 0, a local max at x is 2, and maybe we'll have a local minimum at x is 3. All right, so we have a couple of turning points, and we have a couple of points of inflection as well. So we should be starting to look at the shape and seeing, all right, we should see concave up until we get to here, concave down until we get to here, and then concave up for the rest of that. Now remember, one thing we emphasised when we were on the back of the board yesterday is that always, always, always between any two stationary points, there will always be a point of inflection. So stationary here and here, point of inflection, stationary here and here, point of inflection. Okay, so let's draw the sign diagram of the first derivative. And what we can see is we're decreasing until we get to x is 0. So we have negative slope until we get to x is 0. So for the first derivative, just think about slope. Don't think about those points of inflection. Don't think about the concavity. We're just thinking about, all right, negative slope to there, positive slope till we get to x is 2, negative slope till we get to x is 3, and then we have a positive slope after that. All right, and then all we have to do is draw a graph with these features. It doesn't need to be perfect. So what we've got is it's below at 0, and then it's above, and then it's below between 2 and 3, and then it's above. So it's doing this kind of thing. Okay, good. So that is the graph of the first derivative. Now let's go on to graph the second derivative. So for second derivative, the question we go is, where's those points of inflection? Where's it concave up and concave down? So we have a point of inflection here at x is 1. and we have a point of inflection here at x is 2.5, right, halfway between 2 and 3. And it's concave up until we get to x is 1, and then it's concave down between 1 and 2.5, and then it's concave up after that. Alright, so then what are we doing? Just drawing a graph with those features. X is 1, x is 2.5, and then it goes from above to below to above. Alright, just re-emphasize that point. Points of inflection, here's one, correspond with the turning points. Okay, there's a point of inflection, there's a turning point. Now what this means in the context of the problem is, this will pop up as well, is that's where the slope is maximized. Points of inflection have the steepest slope over that interval. If you're walking along it, okay, it's getting really steep, and then the steepness starts to plateau off. That's what a point of inflection is. So points of inflection always correspond with the largest slope, okay, the maximum slope, or the most negative slope, the minimum slope, right? So that's always the steepest point. Again, points of inflection correspond with turning points, correspond with roots, okay? There's the root at x is 1. Really good, okay. Now, in question 2, it's a little bit different because in question 2, we're given the first derivative. For each graph of f dash of x below, sketch a possible graph which could be f of x. Alright, so we have here from -3 to 1, doing this kind of thing. Alright, and here's -3. This is x is 1. Sorry. Okay, now this is the slope function, and the turning point here is going to be important. Let's call that my x is -1. Okay, that turning point. Alright, sketch a possible graph of the original function. Well, first let's just draw a sign diagram of the derivative function. This is our derivative function, and what we can see is we have positive slope. So we're not thinking about the steepness of this line, we're just saying when is it above, when is it below. Why? Because this is the derivative function, that's what we're told. This is the slope function, and we can see it's above until we get to -3, and then it's below until we get to +1, and then it's below again. So when we think about the original function, what that means is we're increasing until we get to -3, and then we're decreasing. Okay, so increasing until we get to -3, and then decreasing until we get to 1, where it goes horizontal. The slope is horizontal, the slope is 0 at that point, and then it keeps decreasing again. Now the shape of this will be the same, but its relative position on the y-axis is the thing that will change. Okay, so we don't know where it is above and where it is below the x-axis, but all we know is that it's increasing until we get to -3. So we could draw it here or we could draw it completely below. It doesn't matter. This is where it's a possible graph of the original function. So we're increasing until we get to -3. That's at x is -3, and then we're decreasing. Okay? And we're decreasing until we get to x is 1, where it goes horizontal, doesn't it? Sorry, I've got to try to fix that a bit. It goes horizontal, and then it keeps decreasing again. I might try and exaggerate this feature a bit better. So I was doing this down, and then curving down. Okay, so let's explain that from the graph. This is the first derivative of this function. Alright, we have positive slope on the original function until we get to x is -3. Then we have a negative slope until we get to x is -1, and then we have negative slope again. Now I said we don't know its roots, we don't know its y-intercept. That could be located anywhere up and down on the axis. The point is, these features remain the same. Alright, there's one more feature that we can label. Now remember we said points of inflection on the original function correspond with turning points on the derivative function. So we have a turning point here on the derivative function, corresponds with a point of inflection on the original function. We have a turning point here at x is minus 1. That means we have a point of inflection when x is minus 1. We can see that feature. Concave down, concave up. Okay, point of inflection, and then concave down again. All right, we have one more example to do together. So this is example B. And it says, minus 2 and positive 4. Okay, so this is the slope function. So we're going to sketch the sign diagram of this slope function, right? So what we can see, I've got some background because he doesn't filter those out. So what we can see is it's below the x-axis, it's above the x-axis, and then it's below the x-axis. That's at x is minus 2. We can also see a turning point here at x is 1. So what that means for our original function, all right, is we have a negative slope until we get to x is 2. So it doesn't matter where we draw it, like we can do it here. Negative slope until we get to x is 2, then we have positive slope until we get to x is 4, and then we have negative slope. All right, negative slope until we get to x is 2, minus 2, sorry. Positive slope until we get to x is 4, and then negative slope after it. So that's the original function, and we can see its position on the y-axis can change, right? We can move it up and down depending on other constraints that we're provided with, but we've got the general shape of it. Where's the point of inflection? At x is 1, very good. Remember, points of inflection on the original function correspond with turning points on the derivative function. Here's our turning point, x is 1, so that means we have a point of inflection at x is 1, and we can see that that's necessarily the case because concave up and then concave down. All right, we can see that's where it changes shape. Really good. Okay, so let me hand this booklet out to you guys. And I accidentally printed like 40 copies of it last year, so I've been holding on to it for a long time. So on the front page, we have a question that you guys are going to do today. Okay, that's where we're going to dedicate our efforts first. Following that, I'll just take you through this booklet. After you've done that first question, the rest is, it's a bit like the first principles problems, it's a bit like the conjecture problems. You can sort of just have a go as we're moving through them in your own time. All right? The only one that you won't be able to access is question 2, but we're doing 3E kinematics tomorrow, so you will be able to access that tomorrow anyway. So just flicking through, these are all graphing relationships questions. They like to ask it in lots of different ways, but all we've drawn out for you is the relationships, and now what you're going to be doing is recognizing it in a variety of circumstances. So some of them are easy, some of them get challenging. You'll see them lots in the practice tests. You'll see them, you definitely guarantee one in the test that we're going to give you, and it's very likely to be in the exam. So let me give you a bit of an order of what I would like us to do today. And then it's really up to you where you dedicate your efforts, whether it be finishing off what we up to D.1, or whether it be doing a few more of these. So let me start this.